All right, let's continue working with some more examples of integration. Integration is probably my favorite part of calc. There are many rules that you must remember, but it's not that bad. It's not that terrible. I mean, it gets very difficult. If you take calculus 2, you're gonna see a lot of the applications, especially as it relates to physics. In this class, we're gonna see some applications as it relates to area, um, which is gonna come probably in the next couple of lectures. Anyway, let's do an example. Let's say somebody tells you to find the integral of blank dx, where you don't see anything inside. If you see something like this, what it's really going on is that there's a 1 in here. So you're asking for the antiderivative of 1 dx. Now, you may think that this does not fit our rule of x to the p dx equals x to the p plus 1 over p plus 1, but it actually does, because remember that x to the 0 power is equal to 1. So instead of writing 1 there, you could write x to the power 0 dx, because they're equal to one another. And now you could actually see that this does work, because now you could see that this is equal to x to the 0 plus 1 divided by 0 plus 1 plus c, which is equal to just x to the 1 over 1 plus c, which is just x plus c. So we have that the antiderivative of 1 dx is just x plus c. This is true. So let me write this. This is also true. I mean, there is just a variable. So if somebody gives you like blank d theta, this is just, theta plus c. Somebody gives you, blank d phi, that's just gonna be equal to phi plus c. It's just gonna be the case. This is gonna be the case. All right. So let's move on to the other example. Example number 2. Well, what if somebody tells you to find the integral of x plus 2 dx? Well, if you remember, when we took derivatives, we were able to split up the derivative, like I did it in the previous section. So if I had dx of, let's say, a plus b, where a and b are functions, then that was the same thing as dx of a plus dx of b. So the same is true for the antiderivative. We could actually split it up as the integral of x dx plus the integral of 2 dx. And this is very useful, because now we can see that this integral is going to be doable. First of all, let's work on one of them at a time. The integral of x dx is going to be equal to x to the 2 over 2 by the rule plus c, plus, and now we're going to work on the second integral. For that second integral, using the constant multiple rule, if you pull out the 2, you get 2 times the integral of blank dx, or just 1 dx. Well, we now know what that is equal to from the previous problem. That's just x plus c. So we have that this whole thing is equal to x squared over 2 plus c plus 2 times x plus c from before. So it's equal to x squared over 2 plus c plus 2x plus 2c. So we have x squared over 2 plus 2x plus 3c. But remember that because c is any number, it is cumbersome to actually write 3c, so we just write it as 1c. This is x squared over 2 plus 2x plus c. This is perfectly fine. And again, much like I did in the previous part of this lecture, this is the only time that I'm actually going to write it like this, where I have multiple c's in here. In the future, what we will do is we simply will just take the antiderivative of the variables or the constants and just add the plus c at the end. Okay, but this is the antiderivative, and if you want to check it, you could check it. If you take the derivative of x to the 2 over 2, you just get x, and if you take the derivative of 2x, you just get 2. So that's in fact what we had, x plus 2. So we can split the integrals up. So this is very useful. All right, so let's do one more. uh, let's see. Let's say you have somebody in the train gives you the integral of 3x to the 4 minus 5x squared plus x dx. Now here, it's you could actually, now that we know this, we could actually move a little faster. Why? Because now we know how this is gonna work. Um, so if somebody on the train came to you and gave you something like this, then you know that the antiderivative is gonna be, I mean, you could still take it step by step, but this is gonna be 3 times x to the 5 over 5 because of the rule, p plus 1 divided by p plus 1 minus 5 times x to the 3 over 3, because again, you're just adding 1 to the exponent and divided by the new exponent, and plus x squared over 2, and then the plus c at the end. And this would really be your solution. I mean, you could multiply, you get 3x to the 5 over 5 minus 5x cubed over 3 plus x squared over 2 plus c, but this is your solution. The antiderivative of 3x to the 4 minus 5x squared plus x is 3x to the 5 over 5 minus 5x cubed over 3 plus x squared over 2 plus c. So notice that I did that much faster, obviously because I know how to do it. But if you're still practicing, then you should definitely split them up. You could have split this up. So let me write or. You could have done, f of 3x to the 4 dx minus f of I'm saying f. I mean the integral of 5x squared dx plus the integral of x dx. So you could have done it this way, then use the constant multiple rule, and then you'll see that you get the same solution because this integrals are precisely what I have here in parentheses. Those integrals are this, and this. Those antiderivatives are equal to that. All right, let's do another example. Let's say somebody gives you, let's say you're walking your dog in the morning, like 6 in the morning before you go to work, and your neighbor gives you this, and they ask you to find the antiderivative of x plus 1 divided by square root of x. This is much more complicated than what we've been dealing with. Now, somebody gave you something like this, the first step you should do is always try to rewrite it so that you could simplify. So one way of doing this is to write it as x over square root of 5 plus 1 over square root of x dx, because this is now going to allow us to split up the integral and then work on them independently. You can also rewrite the square root of x's as x to the 1/2 dx. So you could do that. And then what I would like to see you do is to split the integral up so you could work on them independently. So now we're working with two integrals, we're looking for two antiderivatives that when we sum them up will give us the antiderivative for the full integrand that we began with. Now, if you remember from the rules of exponents, we have x to the 1 minus 1/2 because of the rules of exponents. This is going to be 1/2. So this is x to the 1/2 dx. When you divide the same basis, you subtract exponents. And then here we just rewrite this as x to the minus 1/2 dx. And now we see that for both of these, the power rule that I gave us is going to work. So the antiderivative of x to the 1/2 is going to be x to the 3 over 2 over 3 over 2. We did this before. You add 1, so this is the same thing as adding 2 over 2, top and bottom, plus, and here we subtract 1/2 from 1, so it's going to be x to the 1/2 power divided by 1/2, because 1 minus 1/2 is 1/2. or negative 1 half plus 1 is 1 half. And again, remember the plus c. And finally, you just have to fix this up a little bit because we don't want to have a complex fraction here. So this becomes 2x to the 3 over 2 over 3 once you do it, plus 2x to the 1 half plus c. And that will be your solution. You could try to rewrite it and factor and whatnot. You don't have to, but you could do it. It wouldn't be too big of a deal if you did. All right. Let's do another example. Let's say now, you're cruising on the street on your 6'4", and somebody gives you the following. Somebody gives you sine of x, the integral of sine of x over cosine square of x dx. So now this person gave you a trigonometric expression here. Now, again, we do not have any rule for this. So what we try to do is to first rewrite to see if we could come up with something better. So if I rewrite this, I could write this as sine of x over cosine of x. Remember, it's a square in the bottom, so I could actually do this times 1 over cosine of x. When you multiply across, you're just going to get sine of x on the numerator and cosine square on the denominator. Now, because this is multiplication, I cannot actually break up the integral. I cannot say, okay, let me do the integral of this and then the integral of the other. Can't do that. But notice that this first expression here, sine over cosine, is the same thing as tangent. It's actually tangent of x. And if you remember your trigonometric identities, 1 over cosine is the same thing as secant of x. And we're multiplying them. We have secant of x times tangent of x. Now, if you don't remember, let me remind you of something. The derivative of secant of x dx of secant of x is equal to tan x times secant of x. This is something that we did way earlier in the semester. Way earlier in the semester when we first began talking about derivatives. So we had that the derivative of secant of x was tan x secant of x, so that means that this antiderivative is simply equal to secant of x plus c, because we know that the derivative of secant of x is precisely tan x times secant of x. Order doesn't matter because multiplication. You could also see it as secant of x times tangent of x. But again, it's multiplication, so the order doesn't matter. All right. So sometimes, so far we have seen that the equation of y equals the integral of f of x dx has many solutions. Because of that plus c, we know that there's infinitely many antiderivatives. Now, it is actually possible to find a particular solution. What do I mean by that? It is possible to find a solution for the antiderivative for which we get a specific value of c. Okay? So, for example, let's say somebody gave us the following equation, y equals the integral of 3x squared minus 1 dx. By the rules that we have so far, we know that this is actually equal to x cubed minus x plus c. If you don't see it, remember x to the p plus 1 divided by p plus 1. We have a 3x squared. Well, what happens here is we have 2 plus 1 divided by 2 plus 1. Well, 2 plus 1 is 3, so we have 3x to the 3 over 3, but the 3's cancel, so you get x cubed. So this is the antiderivative. Now, we know that for every single c, An antiderivative is given by the differential equation, which is dy dx equals to 3x squared minus 1. This is the derivative. This is the integrand over here, but that's the derivative of this, 3x squared minus 1. And from the first part of this lecture, we spoke about how the antiderivative is not necessarily unique. Now, if we wanted to find some particular solution, then we need a value for capital F of x. So because we have a function, we know what the function is. We have a function that is, let's call this capital F of x is equal to x cubed minus x plus c. We know that this is going to have some graph, right? It has some graph. If somebody is able to give you a point on the graph, like let's say somebody gives you a point on the graph P, and they tell you that this point of the graph is equal to, let's say, 2, 4, then now you know that whenever you plug in 2 to this equation, regardless of what c is, you get 4. So we can actually solve for this and get a solution for the whole equation, because we have what the antiderivative is. We have x cubed minus x plus c, and that is f of x. F of x is x cubed minus x plus c, the antiderivative. But now we know that when you take f and you evaluate it at 2, you get an answer that's equal to 4. So we have really f of 2 is equal to 2 cubed minus 2 plus c. That has to be equal to 4 because the 0.24 is given. And that means that 2 cubed is 8 minus 2 plus c equals 4. I should actually do this. So we have 8 minus 2, well, that's 6, plus c equals to 4. If we minus 6 on both sides, we have that c is equal to negative 2. So now we have found a particular solution for the antiderivative, because now we know that f of x is equal to x cubed minus x minus 2. So this is a particular solution for f of x. This point that I gave us is called the initial condition. So if you're given an initial condition, it is often possible to find a particular solution of the derivative. So for example, let's do another one. Let's say somebody asked us to first find a general solution, then find a particular solution that satisfies, let's say, f of 0 equals 3. And the derivative given is f of x equals to e to the x. But first of all, remember, to find the particular solution of this, we're given a derivative. So what we're given is the following. We're given f prime of x dx. We have to find out what this is equal to. Remember that from what I told you earlier, this was just equal to f of x. This is one of the first things that I wrote on the previous part of this lecture. So what we really have here is the antiderivative of e to the x dx, which is just e to the x plus c. So this is the general solution. This is the general solution here. Now, if we use the initial condition said that f of 0 is equal to 3. That means that when I plug 0 in for x, I have to get 3 in my f of x. This is capital F of x. So that means that what I have here is, let me first write it. F of x is equal to e to the x plus c. When we evaluate it at 0, we have e to the 0 plus c has to be equal to 3, because that's what's given. So we have that 1 plus c is equal to 3, because remember, e to the 0 is 1. And then when you minus 1 on both sides, we get that c is equal to 2. So the particular solution is f of x, capital F of x, is equal to e to the x plus 2. Okay? And let me just, maybe I should show you real quick on GeoGebra what's going on. So what do we have? We had e to the x was what we had first. So e to the x. Yep, I'm hitting the wrong thing. Let me fix this. So we have e to the x, right? That's our, so that's e to the x plus 0, right? But then we could also have e to the x plus 1. Notice how that shifts up the function up 1. We could have e to the x plus 2, which is what we had as a solution. If I'm not mistaken, let me just double check. Yeah, we have e to the x plus 2. So the red one is the solution, the particular solution that we had. We could have also had e to the x minus 1. We could have had e to the x minus 2. And notice how our original equation is just e to the x. If you take the derivative of all of these other graphs, you're just going to get e to the x. You're just going to get the green line. So whenever you take the derivative, these constants go away and you just get back e to the x. So there's only one antiderivative that we get from taking the derivative of all of these, but we could actually find particular solutions if you're given a point on the graph, on the original graph. So you could actually find exactly which antiderivative you're looking for. So that's what I'm referring to. Okay? So this particular solution gives us the exact function that we are looking for. In this case, e to the x plus 2. Finally, one of the most important parts of this section is talking about these accelerations, the acceleration and velocity problems. So, for example, let's say let's see. If I could get a good example. I guess this example should suffice. Let's say you have a ball that is thrown upwards with an initial velocity of 64 feet per second from an initial height of 80 feet. Now, we are asked to do two things. One, we want to find the position function that gives the height x as a function of time t. And two, what we're asked to do is we're going to find when does the ball hit the ground. Okay, so first of all, we did an example similar to this earlier in the semester. We talked about position functions before. So let's say s of t is our so-called position function. we saw that the derivative s prime of t is the same thing as the velocity of t. So this was the velocity function. So when we took the derivative, we get the velocity. And then when we took the second derivative, when we took the derivative again, s double prime of t, we had the acceleration of t. So this is the so-called acceleration function. So in this particular problem, we are told that we begin with some initial velocity and some initial position. So instead of working, from the top down, from the position, velocity, and acceleration, we're actually working from the bottom up. So instead of taking derivatives, we're going to be taking antiderivatives. So first of all, let's let the variable t stand for time, and let that be equal to 0, so that this is the initial time. So let t equal 0 represent the initial time. Now we have two initial conditions. We have that s of 0, because at the initial velocity we were given, s of 0 is going to be equal to 64. I'm lying. S of 0 is the position. So the position was given to be initial height of 80 feet. So the position is 80 feet. And s prime, which is the velocity, is 64 feet per second. Now, for the acceleration due to gravity, we will use negative 32 feet. And you may think that this is coming out of nowhere, but if you look at the function for gravity, then you will see that it is actually equal to this. So let me actually write it down. So the position for gravity is 1/2 g of t squared plus v0 t plus f0, where v0 is the velocity, s0 is the position, and this g is equal to negative 32. Okay, g is equal to negative 32. That's gravity. V0 is the velocity, and s0 is the position. So if you take the first derivative of this, of s prime of t, you're gonna get just g of t plus v of 0. And if you take the second derivative again, that gives you the acceleration, you're just gonna get g. But g is negative 32, so the acceleration is negative 32. So that's where I get this negative 32 that I'm gonna be using. So using negative 32 feet per second as the acceleration due to gravity, this is a nice formula to know, this gravity formula. It's used in all of physics. Due to gravity, we can write s double prime of t is equal to negative 32. That's what I have here. S double prime of t is equal to g, but g was equal to negative 32. So that's exactly what I'm writing here. So I'm beginning with the second derivative. Okay, so if we want to find out what the first derivative is, so we here, this is the acceleration. If we want to find the velocity, because remember we're going up to position, then I have to take the integral of s double prime of t. We have to take the integral of what came before it. Also notice that I'm using dt because that's the variable that I'm integrating with respect to. So now if we were to look for the antiderivative of this, remember that s double prime of t is just negative 32. So this is going to be equal to negative 32 dt. But again, this is the same thing as negative 32 times the integral of 1 dt. which we know is negative 32, this antiderivative, remember, is just going to be t plus c. So remember, we did this before. We have the integral of blank dx is just x plus c. So if we have the integral of blank dt, it's just t plus c, and then you multiply by negative 32. So you get negative 32 t plus c. So this is s prime of t. Now, if we use the initial velocity that we had, remember we had an initial velocity. The initial velocity that we had was s prime of 0 equals 64 feet a second. Now we have a function for that velocity. We have s prime of 0 is equal to negative 32 times 0 plus c, and that has to be equal to 64, because that's what we had up here, that the initial velocity is equal to 64 feet a second. So to find this particular solution, we have negative 32 times 0. Well, negative 2 times 0 is just 0, so we have that c is equal to 64. So here we have that c is simply equal to 64. So now we can rewrite s prime of t, the derivative or velocity, as negative 32t plus 64. Instead of plus c, notice that now we got rid of the plus c, and we were able to substitute the 64. Okay? So this is what we call C1, because it's the first c that we solved for. Now to find the position, we again find an integral. And the integral that we will look to solve, so to find the position s of t, we have to solve for the integral of s prime of t dt. Remember, this comes all the way up here. Instead of taking derivatives as we go down, we're going up. So we began with the acceleration, we took the antiderivative, we got the velocity. Now that we have the velocity, if we take the antiderivative again, we will get back to the position. So let's see what we have here. We now have that s of t is equal to the antiderivative. We already know what s prime of t is. S prime of t is negative 32 t plus 64 dt. And we could actually find this antiderivative quite easily, because this is going to be negative 32, the integral of t dt, plus 64 times the integral of blank dt. So this is equal to negative 32. And remember, the antiderivative of t is t squared divided by 2 plus 64t plus c. Because remember, this is just going to be t plus c, so you multiply the 64 times t. Now, negative 32 divided by 2, I believe that's negative 16 t squared plus 64t plus c. And we have a value for an initial value for s, for the position. We have s of 0 is equal to 80. This was given in the problem. So now we can say, because we have found what s of t is equal to, that s of 0 is equal to negative 16 times 0 squared plus 64 times 0 plus c has to be equal to 80. Well, negative 16 times 0 is 0, 64 times 0 is 0, so we get c has to be equal to 80. So now we have, and this is c2, so now we have that s of t is actually equal to negative 16t squared plus 64t plus 80. So we have now found what the position function must be equal to. Now, we were asked to find a position function. That was part 1. So we did all of this work to find part 1, to find the position that gives the height of the function of time t. Part 2 is to find out when does the ball hit the ground. Now, the ball hits the ground when this function is equal to 0. Because if the position is equal to 0 and position is positive, then the lowest possible position that you could have will be the ground, and that will be 0. So all we have to do is solve for when negative 16t squared plus 64t plus 80 is equal to 0. Now, believe it or not, you could factor out this in a quite nice way. Is actually equal to, if you factor out negative 16 times, let's see, t plus 1 and t minus 5. Let's say if you multiply t times t, you get t squared. Then you're going to get in the middle negative 4t and then negative 5. And then, yeah, if you multiply t squared by negative 16, you get negative 16 squared. If you multiply 16 by 4, by negative 4, you get plus 64. And then if you multiply negative 5 times negative 16, you do get 80. So that is correct. So we get t plus 1 equal to 0, or t minus 5 is equal to 0. So we have either t is equal to negative 1 or t is equal to 5. But remember, the position has to be positive because you cannot go lower than the ground. You know, if you're dropping the ball from here, let's say this is 80 feet, and that ball is supposed to be going down to the ground, this has to be 0. You cannot go lower than this unless you make a hole in the ground. So this answer, we do not care about. The correct answer will be t equals 5. So we can say that the ball hits the ground after 5 seconds. Remember, t was time in terms of seconds. And we're done. So we have found out by using the antiderivative what the position function is, and we began from the acceleration function, and we were able to find when the ball actually hits the ground. This is a problem that will definitely be on the final exam for this course. There are plenty of practice problems about this on the homework and on the book. So I highly suggest that you look at the homework problems, look at the book, and look at the lecture notes that I also have posted on Blackboard. This is the end of this lecture. Thank you for your time.